So this is going to be the second lecture of Wolfgang Lueck. It's going to be on the possible values of the L2 invariance. Wolfgang.
So thank you very much again. In some sense, I will try to get even more algebraic in this talk. But I want to emphasize there's a lot of analysis behind this, which I also like and love, but we can't do everything. I was only allowed to give 2 talks.
You can come back.
No. Okay, so let me come back to the von Neumann algebras. So review that we actually I will only look at discrete groups. I didn't say that, but it's unfortunately all I can do. We call the von Neumann algebra, which was defined to be all bounded operators from L to G or L to C to itself. And from now on, I will only consider it as a ring. I will forget the topology. This is not a bad idea, as you will see later. The definition was topology, but now we are purely to algebra. So when I say module in the sequel, I mean just a module over the ring of the von Neumann algebra. Not any war here, but modules whatsoever. We call it, we had this nice trace from the von Neumann algebra to C. Write it down again. Operator goes to this inner product. And if you write this operator as a formal sum, you're looking at the coefficients of the identity. So now I start with a finally generated projective module. It means it's a direct summon in a free module, which is finally generated, so I can choose a matrix over the von Neumann algebra, which is idempotent. And the amorphism of the free ng module n to free module operator n here has an image, and this should be just as modules over the von Neumann algebra or projective module. And then you can define the dimension of this projective module just to be the trace of this matrix. Actually, what I'm doing here is really runs under Hattori's tonic. I have nothing to do that my trace comes from a von Neumann algebra, so it works in general. Last reminder about the last talk, the category of these modules in algebraic sense is actually the category of finely generated Hilbert ng modules. There's an equivalence of categories, therefore I can really pass to the algebra here, not losing any information. Okay, now algebraically you can, first of all I have to write down a slogan. The slogan comes in, let's say, first version. The first version is don't be afraid of von Neumann algebras. The second version is actually even harder, nicer. So ng behaves like a very friendly ring, namely the integers. Of course, except it's not material. And has a lot of zero divisors.
Maybe should be who's afraid of the big bet von Neumann algebra.
What makes this precise? But I would also give you a way in some sense. You see, when you do mathematics, you always have to have the baby example. And my baby example was integers, I'm not kidding. So when I write down our theorem where I extended certain dimensional functions, I was staring at z. And then when I got convinced that the slogan is true, I could do what I want. Before I was not convinced psychologically, I couldn't do it. So for the young people, mathematics has a lot to do with psychology. Like in sports. Okay, so what I want to do next is, I would like to extend this dimension here to all modules. This is a key observation in many, many things. So observe here that I have defined this condition, but it turns out that I can define this for all modules. And this is the next really important theorem. But first of all, what is the slogan here? So the bad news is Ng is Noetherian exactly if G is finite. So we should not really should use Noetherian at all. And you may ask when it has zero divisors or not. This is even more precise. There's only one group, even then G is already trivial. So really should not use anything about Noetherian or zero divisors. But then I'm saying the rest is true. So what is the good thing about the integers? It's a principal ideal domain. And that survives in the sense that Ng is the so-called semi-hereditary ring. I see what it is. Recall what the principal ideal domain is. It means any ideal is free, Witten generator, and this means simply any finitely generated ideal is projective. Or more, hereditary without semi means that any submodule of a projective is projective again. And when you see semi means you have to take a finitely generated submodule of a projective and it's projective again. That's a very nice property. And this is the basic to come to the next theorem, the next part of the theorem. So there is a dimensional function. Which is defined for all modules. And therefore you must allow the value infinity. You can imagine take direct sums, but you will see this is not very often attained. That's the good news. But what are the properties? Which is uniquely determined by the following properties. So something let pretend is Christmas, so what do we want from a dimensional function? Right? It should be additive. So when we have an exact sequence, we would like to have a formula that in the middle, and thus omit the index of the formula, is the sum of the outer dimensions. And infinity plus a number is infinity. Then I would like to have what is called cofinality. So in other words, if I can write a module as a directed union of submodules, directed, then I would like to have a formula that I can compute the dimension of the union as a supremum of the dimension of the modules appearing in the union. Well, this makes sense, right? Because of additivity, the dimension of Mi is at most the dimension of M. You would like to get it when it's exhaustive, you get everything. Then there's a property continuity, which I should say what it is. Suppose M is finitely generated. K in M is a submodule. And then I can define a kind of closure, kind of Zariski-like closure. If I look at all elements in M with the property that f of x is 0 for all possible functionals on M which vanish on the given module K. Roughly speaking, closure means I will not be able to distinguish any element here from its closure by testing by functionals. Right. So algebraic geometry would mean that you look at polynomials. Here look at any functional. And another point then is you can look at the closure of 0 which is called the torsion part. We may look at this quotient. So m divided by the torsion of m. Then it turns out that you also have a resolution of the torsion part. Dm is finely generated projective. And here the conclusion is that the dimension of the closure is the dimension of the thing I started with. And here the conclusion in this particular case is the dimension of m is the dimension of this projective part. But I forgot to mention, of course, at the very end, this extends the given function. On finely generated projective modules. So now let's think about the case of the integers, and you understand what's going on here. This here is one of the fundamental theorems of abelian groups. If M is a finely generated abelian group, the torsion part of it is actually those elements which are not detected by maps to Z. Of course, the quotient is even a free module. I only get projective here. This exact sequence is obvious, and this resolution is also clear. If you think about a finely abelian group, you always get an extension and a resolution by Zn to this torsion group. So this is very much like an abelian group case. And in the abelian group case, you know how to extend this. If you think about it, if you have an abelian group, what is its rank, you tensor it with Q and takes the rational dimension. And this function would be the same thing here if you would replace Ng by Z. Always we had all these properties. The good thing is this works for the phenomenal algebra as well. But the main important thing is that for your phenomenal algebras, you often, very often, have even a real number, although your module is not finely generated. That's the big difference. Why this theorem for the integers is rather useless is very important for the phenomenal algebras. And now you can do a fairly obvious game. Now recall the definition of the ordinary Bethe number. Now I can get even closer to this. So let X be any bar G space. And I mean really any. The action doesn't have to be free, it can be anything. Of course, I'm still possible to look at the singular chain complex of X bar, which is now a module over the group ring. I tensor it up to the phenomenal algebra. So I'm getting a chain complex, a huge one, over the phenomenal algebra, that is the ring. Takes the homology in the classical sense. There's nothing special anymore about closures if you remember, and takes this new dimension function. And this could be defined as the algebraic number of X bar. But in general, it could be an element which takes really infinity. And now for a group, it's clear what I will do. When I write down a group, I just take this number for the classifying space of the space G, the total space of the universal G bundle. And it's also, for instance, now clear this is a homotopy invariant, a geomotopy invariant, because the homology is. And very important, if we have a G covering over a closed Riemannian manifold, then this definition reduces indeed to the one we have started with. And to make it clear, it's really this limit I was writing down for t goes to infinity of an integral over a fundamental domain of the heat kernel on the corresponding carbon. This is very, very useful. You can imagine now you have all flexibility in algebraic topology. One example is You remember I was writing down this theorem where I said the first Betty number is trivial. You may remember that some nice applications. This is actually an application of a linear spectral sequence to the corresponding vibration. And now I can set up the sequence because it's all algebraic. If I would do this in the category of Hilbert spaces, I have the problem, I have differentials. I can't do it anymore because I can't take kernels in the way I would like to do. So this flexibility was actually one of the main keys in the proof of this theorem. But we will use it further now when I would like to talk about possible values of Betty numbers. And I would like to send the message from the very beginning. This question is related to algebraic K-theory, which I think is a very nice new connection. But I would like to explain this next.
Can I ask why you've taken the L2 Betty numbers of EG and not BG?
Because I want to have a G space.
Oh,
So,
yeah,
I would go to universal cover, and universal cover of BG is EG.
Okay.
Right? So I could also, if you like, have written it, then it's maybe more familiar, if you like. Okay. Okay, now we want to understand what are the possible values of these dimensions. But of course, coming now from the group ring. You see, geometry starts always with the Celler chain complex over the group ring. And therefore, when you're asking now what are the possible values of Betty numbers of dimensions, you should start with the module of the group ring, induce it up to the von Neumann algebra, and figure out what is the possible dimension. That is now the key question. So therefore, I will introduce the following notion. So we start with a field between Q and the integer and the complex numbers. Usually in this talk, I think F will be C or Q. And then I introduce the following subgroup of the real numbers. And it's the additive subgroup. And what I will do is, I look at the dimension. I will now omit the n of G all the time. Where I use up a module to the von Neumann algebra and take a difference of these two things. And M0 and M1 are modules over the group ring. So the F enters here, it could be Q or C, having property question mark. You have to tell you what I will look at. Right? So, of course, the weaker this condition is, the larger the group will be. And what are the things we would like to investigate for this question mark? There are the symbols F, G, P. I will remind you always when I use it. It's a finely generated projective. That's the smallest class. I could also write FP, which stands for finally presented. And this will be the class we want to investigate later, because this comes from geometry. I can go further, only look at finally generated. And then I could say all. It's not really all. I would just assume that this dimension is finite. So the difference is here and here that I will require that these modules are either finite and projective, maybe only finite presented, or even more general finite generated, or just any module, but at least the dimension should be a small infinity, otherwise I can't write down this minus sign. So there's a first obvious interaction between these two. The first part is obvious. I get the following inclusions. if I make the maximal condition on the modules, of course I will have something smaller. When I go to file presented, it can be bigger. If I go to file degenerated, and of course the biggest one is where I would allow all modules subject to the dimension condition. B is that if you look at the finally generated modules, they are sitting in the presented ones closed. That means whenever I have a finally generated module, and know this number, I will find in a sequence of elements in here which converges to this. And the closure, of course, in R. And what you always have is, that if you close everything, you get equality. I will not give the proof, but I give you the key word. It's co-limit arguments. Plus cofinality. So this is, for instance, obvious here. Suppose I start with some module. I have no idea where it's finally generated. But I can write it as a as the union of all finally generated submodules. But this means that the dimension of this big module is a limit of the dimension of the finally generated submodules, and therefore these closures are the same. Essentially, it's only arguments like this. This is really not very hard to figure that out. So now I would like to first say something about this. Then I will explain why this is you would like to understand for geometry reason. And then I will say why some guesses are right or not right, depending on what you are doing. Okay, let's focus on this first, and there we have a clear conjecture statement and theorem. First of all, I have to explain this notion when I write something like this. I mean the abelian subgroup generated by possible orders of finite subgroups.
So I can't read what is this, the letters underneath the one there?
Here, the finite.
Finite.
Finite. So I'm looking at all finite subgroups. Take 1 over H, but I'm not localizing. I'm taking only the additive subgroup generated by these numbers. So yeah, okay. I'll give examples in a second. And the conjecture is, this conjecture is open, no one knows the counterexample. It has been proven for certain classes of groups. If there is an upper bound on the orders of finite subgroups, then we expect that all these things degree and are equal to that. So when we expect that this subgroup of the reals is what we would get if we plug in, for C even, finally generated projective modules, could go to finitely presented modules, You may even look at finely generated modules, or actually look at all modules. Let me spell out what it means if G is torsion-free. Then this here is just the integers. Because I have only triple group, it's the abelian group generated by 1, it's the integers. Also observe that this group here is a discrete subgroup of the real numbers. That's one important thing, why I never have to go through this closing business anymore. That's the reason why I expect everything to be the same. So what is now the reason why I personally believe that this conjecture is simply true? Here's the result. Let's say if the map given by induction so now I'm taking the direct sum over all subgroups of G which are finite, takes their class group. Recall, this is a so-called projective class groups. Elements are given by finely generated projective modules, and the only relations are these typical exact sequence relations. And if H is finite, this is the same as a complex representation ring of H. You may be familiar with that. And whenever you have a subgroup, you can deduce up. So you always can come to K naught of CG. Plus H is a subgroup in here. Take all the possible maps you get by induction. And if this map is surjective, then this conjecture is true. This conjecture there. So how is this proven? Here you start with your module M, which is finely generated projective. And actually this dimension function I mentioned in the very beginning gives you a nice map from the projective class group to the real numbers. You just send a module to its dimension. So now I take, maybe called P also. So if I want to compute this dimension, I have to check what is the image of this map, that's all. But now everything comes from here, right? So I can write an element in K naught of CG as a sum of finely many elements coming from K naught of CH for some finite subgroup. So if I can show that the following composite has as image 1 over H times integers, we are done. Right, because I take an element in here, I can write it as a direct, the finite sum of elements coming from different subgroups here. So I see I take n times one order plus m other order. This is just what needs to be the being generated by these elements. And the point here is that this comes from the following lemma. So when you have a subgroup, this is in general true, H and G, then first of all, NG is faithfully flat over NH. That means if you have an exact sequence in, if you have a sequence in NH and then use it up, it's exact upstairs exactly if it is upstairs before, downstairs before. So it's the best you can get. And moreover, the dimension satisfies the formula you're hoping for. if you induce a module up from H to G and takes then the dimension, I can just take the dimension on H level first and that's it. And now you see that this means that this composite has this image, the image of the dimension function for H. But now H is finite, and you may remember that the dimension for the final group is simply the complex dimension divided by the group order. The complex dimension is always the integer in the given up. Okay, and then I should, we're not really saying so much about it, so remark. So this map, surjectivity, is known for a large class of groups. And I think it's enough if I can give you some oral indication. What I'm really after here is the experts. I would like to know that the Fair-Jones conjecture is true for our group G, which is the k-theoretic version of the Baum-Kohn conjecture. And meanwhile, we have proven the Fair-Jones conjecture for many, many groups. They include hyperbolic groups in the sense of Gromov, cut-zero groups, fundamental groups of three manifolds, arithmetic groups, and all lattices. And also is closed under taking subgroups, direct products, free products, and very important under co-limits of directed systems. And this, for instance, means that all the kind of monsters which are constructed by the group theorists, Tarski monsters or whatsoever, are in this class for which we know the conjecture, because usually these constructions go as follows. You start with a hyperbolic group, you add relations, make sure you always have hyperbolic groups, and then you go to the limit. Yeah, but if hyperbolic groups are in this class and the class is closed under co-limits, the limit is also there. And therefore, all kind of strange groups, as the Tarski monsters, there are some groups with expanders, belong to this class. This is the reason why I really think that this surjectivity is simply true. But this would also mean that we have, that this conjecture is very likely to be true. Okay. But of course, notice it's a moment only at this place where we have finite and projective. Now comes the hard step, which is unclear, to go to there. And now, first I would like to explain why we want to go to finite and presented, because then we have a topological interpretation. So what is this? So this, so if G is finally presented, let's say, then this group, and now notice I take finally presented, right? But I said before there was finally projected. I go here. And this turns out to be differences of Betti numbers where I allow any closed manifolds with the right fundamental group. So if I take all possible manifolds which have G as fundamental group, you get some Betti number of this manifold, take the difference, I get an additive group, it's exactly this group here. So how I give you an idea how this works. This is in here is very easy because I defined it as a homology and a dimension, and the homology is always something which is finally presented. The way back is, roughly speaking, when I have a module here, I can write it as a matrix by a presentation matrix, and then I will find a manifold whose, let's say, 18th differential on the universal cup is exactly this matrix, and I'm done. So it's a kind of passage from finally presented modules, which are matrices, to topology by constructing nice manifolds with the right differential. That is the idea. That's the reason why this is, of course, the thing we really would like to understand. Okay, so the main question that we have to figure out is, what is the difference? Between what we understand rather well. Sorry, here's a Q. It is very important. Because, of course, chain complexes live over the integers, and I can clear denominators, but I don't know what happens with C. So this equality is very important that Q, the complex numbers. So, but I have to understand this difference, where I put finally generated projective versus finally presented. I should say this theorem there is actually also true if I replace C by any field between Q and C. So this conclusion here, I could replace C by any F. I could also write Q for C if I want. This is the key question, which is really behind the question, what are the algebraic numbers of, let's say, a given group G. So now we have a positive part of this lecture and a negative part in sense concerning values. But since you had already talked about thought examples, I will just briefly recall what is known and not say so much about their proofs. I would then like to concentrate on a program, how to prove this conjecture. This. Stronger version of conjecture B is A is the following. Again, if there is an upper bound, or have I written it? Okay, sorry. It's okay, everything is there, but when I wrote down that this is implied, I only mentioned the first equality. So I mentioned the theorem. I said if the co-limit, if the direct sum goes selective to k0 of Cg, is given this equality, doesn't give the other ones. Sorry, I think I've misstated this. But the conjecture as it stands is still what I would like to prove. Then we'll give you later evidence or kind of program how you could prove it, but of course I can't fill in the program, but it looks promising. But first let me say what happens, because in general we don't have this equality. Maybe we look at examples first. Then you see the idea how the count examples are constructed actually. So let's look at the examples of the infinite intermediate group. You may write as Z2 star Z2. Or the semi-direct product of C with C2. All its subgroups which are finite have only 1 or 0. So this 1 of fin of the infinity is indeed given by all possible sums. The m is an integer, and you may divide by 2 or not. And this actually is known that everything is true, satisfies conjecture. That is known. But the next example is, it's kind of baby version of what people like Austin and Kowalski have done. But let's look at the infinite direct sum of copies of Z2. So I'm not passing to the Lamplighter group right now. I just look at this group. Of course, this now has a lot of torsion. Right? It's direct sum. Of course, this number there, 1 over the finite subgroups of this group, Z, turns out to be Z 1 over 2 localized. Right? For any power of 2, I will find a subgroup here which is finite and has the right cardinality. So these are now the numbers of the shape m divided by 2n. So it is known that the localized M2 this corresponds exactly to the point-generated projective ones, actually for any field. And also it's the same for the finally presented. But I will also try to explain why. You see the first step, if you go to finally generated, you get out. So it's not clear why this is true, but the reason is the following. This group is a so-called locally finite group. It means any finitely generated subgroup is finite, and when you have a matrix over it, the matrix lives already over a finite subgroup. Now you can imagine that any matrix here right down comes from a finite subgroup by induction. It means any finite presented module comes by induction from a finite subgroup, and then it's an easy calculation. This here is not surprising because I mentioned that it's surprising, so I have to say something. But what is the idea here? So look at the following subgroup, call it IK. It takes a direct sum in here. So this is a subgroup where you have arbitrary entries at 1, 2, and k, but you have nothing later. And then you look at the following module. It's QG, then there's this subgroup where you take Q, the trivial action. This is now a QG module. And then it turns out that these are nested in one another with a complement. So n-1 is of this shape. And the dimension is an easy calculation of this guy. Is 2 minus n. And these ENs are disjoint. So for any index set in natural numbers, I may look at this joint union. Call this Mj. The dimension of Mj is the sum over all integers in J to the corresponding power of 2. And of course now I can choose my J so that any real number is realized. So that means that especially Qg times Mg has a dimension of, any real number between 0 and 1. This module is finally generated, so I've realized any module. So the point is, when you have infinite torsion, you find a big subgroup which has large torsion. It means you can get a number which is very small, like 1 over n. And since in some sense by these cofinality arguments, you can close these things, you get suddenly new numbers like an irrational number, because the irrational number is the limit of small enough rational numbers when you add them. Of course, now the point is this group here is not at all finely generated. This is, of course, a flaw why people like Austin and Grabowski had really to work much harder. And also with the Gotik Chuk, so let me mention now two results.
Yeah. The summary.
Exactly. So they look at the Lamplighter group, which is the group I started with, cross C. By the way, do you know what's the Lamplighter group?
Okay.
Yeah, exactly. You have these.
Actually, I remember Lamplighters in
Okay.
Warsaw in 1950.
The 2 means on or off, and then the lamplighter goes and switches
That's
and switches. But what is the role of this here? The role is that this is now a fine generated group. Without this, it's not fine generated, but with the Z, it's fine generated. Question? Okay. And they give an explicit element, X in the group ring, explicitly, which is actually given by the so-called Markov operator of the Cayley graph of obvious generators. And then they showed that the dimension of NL of the co-kernel multiplication with X is 1 over 3. They made this calculation actually using this approximation thing, and they had no idea what they had done. because Peter Linnell and I were sitting in the audience and told them, this is a counterexample to a well-known conjecture. And then later they really went through, because they get now these irrational numbers, because we know that if you go to 5-generated projective modules, this is z over 1 over 2. It doesn't contain 1 over 3. Therefore, we have the first example. So what they really showed us, and this is really of significance, that this expression is not the same as if you put 20 presented modules.
So this means that the L2 Betty numbers are not.
That means that there is an L2 manifold with an L2 Betty number 1 over 3,
Yes.
although its fundamental group contains only 2 torsions. Right. That was the contradiction. Still, it was a rational number. That comes now Team Austin into play. When he showed, roughly speaking, of course he showed more, but that was this idea. You look at all these values, but you look at all finely generated subgroups. And this turned out to be uncountable. Actually, it gives you a small group in some sense. But he showed that if you take all the Betty numbers of all finely generated subgroups for finitely presented modules, it's uncountable, therefore it contains an irrational number. Vice versa, it means because you have an irrational number in this union, you find a group G, which is finely generated, for which there is a module which is finally presented with irrational Betty number, therefore it's a manifold, a certain covering, which has the wrong L2 Betty number. And you could actually show more, there exists even a finally presented group. The probability that this is not contained in Q. And he did this in some sense by looking at this group here and looking at all possible. He took an extension with a free group, and the free group he was acting on here. And he was looking at certain invariant subgroups. And then he was showing that for any of the subgroups you get a different number, but there are uncountably many subgroups, so you get uncountably many numbers, and that's it. And then Grabowski came in. Again, he proved also much more, but I would like to make this short for time reasons. There's an explicit example, very explicit example. Of a group G, of an element in the group ring. So that's the dimension of co-kernel of the corresponding map is a number R, and R is also explicit given by a power series. I've forgotten the formula, but very explicit. And the group is small. It's not really a huge group. It's still lamp-lighted type, I would say. So these are the count examples, and I would say probably everything can really happen. Grabowski also showed, for instance, this here unit is the whole, all real numbers. So, of course, now this raises the question, why is it so important to have the upper bound there? So is there any reason why you expect an upper bound? And I will try to explain this now by giving you a kind of program how you could try to prove this conjecture and show in the program where you need this assumption. So the point in this program is what I like to call the magic square. And this goes back to ideas of Linnell, actually, Peter Linnell. All these ideas were buried in a paper, and one of my students, Holger Reich, worked this out, and you can also find a good description in my book on L2 invariance. So we start with a complex group ring, and you have the phenomenal algebra. And this is what you really like to understand, right? You start here, use it up, what we get. Now remember a second about the integers. I said that phenomenal algebras look like integers. When you want to look at dimensions, it's very good to go to Q, which is the quotient field. And here is a candidate for this, the so-called algebra of affiliated operators. I want to say what this is. This comes from function analysis, but algebraically, it's the over-localization for the subgroup of non-zero divisors.
So maybe we should explain, remind people what the order localization is.
Maybe not.
No, all right.
It's a way of going to a quotient field in non-commutative situations.
They're just fractions, but
It's
in
fractions, yeah,
that's
true.
all.
Yeah.
I mean, it's
So now there's a third one called DG. And DG is a so-called rational closure. In the phenomenon, this UG, what is this? This is the smallest ring. It sits between CG and UG. It has the following property. If you have an element in DG, which is unique in the big ring, then it's already unique in the ring itself. So in other words, you start with x, you find in y in u of g so that x times y is identity, and the y is already in here.
you said y, but you had x there. You want the
So then the,
or is it that x? So it's the same
okay,
x.
should, if x is a unit, then
Yeah,
x
yeah.
is already
I see. Okay.
Let me give an example, because, as I said, always look at baby cases. What happens in the case G equals Z? So what is CZ? It's the ring of Heinz-Laurent series. If a normal algebra was L infinity of S1, the algebra of affiliated operators are just now all measurable functions from S1 to the complex numbers. And here, you just get the standard quotient field. A field is obviously rationally closed. Okay, having this, now what's the program? So suppose that G satisfies the following condition. The first one is familiar. We have to have this to be surjective. Second condition is that this map must be surjective. And finally, you want to have DG is C by C. If you check this here, obviously satisfied all these conditions. But why does this really give you the claim? Maybe I like to explain this. Of course, I forgot to write down the conclusion. Say then, conjecture A holds. Of course, I need a bound on the order of Heinz subgroups. bound on the order of fine subgroups. Then this conclusion is clear. Maybe I give you an idea. There are two key observations. One observation is that the dimension function I have defined before can be extended to this U of G. It's not really a surprise. So now suppose I start with a module which is finally presented. So it is here. I push it down to dg. But dg is semi-simple. That means d of g times cgm is finally generated projective. This assumption here. So this ring dg is something responsible for coming from finally presented to finally generated projective. Here it happens. But this means now that I can write my dimension which I would like to understand. It's contained in the image of the map from k naught of dg, k naught of ug to the real numbers. Here's the dimension, here's the change of rings. Because I know the element here is projective, it gives me a class here, and by definition this class here is mapped to the dimension of this class in here, but because this square commutes, I'm done. So in some sense, here the passage from finally generated, from presented to projective happens. And now I use the fact that these two maps are surjective. So if I want to study the image of this map, I can just precompose with these two surjections. So the image without this is the image of this whole connection. Now the same argument appears as before. I start with something over a final group and know pretty well what its dimension is. This is really the connection where you come from this program to there. And just one remark, if you have these things satisfied, this forces to a bound on the order of finite subgroups. So sometimes this program can only work if you have this condition here. And if you look at this program, if you try to go through it without this, you see very well where it really goes wrong with these examples of closure. So in some sense, because you can turn it around, and moreover, I want to also mention if G is torsion-free, this implies that dg is a skew field. And then actually we know what the dimension is. It is the classical dimension of the field, skew field, of this module. Which is of course an integer. And also remember the Kaplanski conjecture, it said there are no zero divisors in C of G. Is a better explanation. CG embeds into a skew field, and a skew field has no zero divisors. Let me finish with two remarks about another question, which is also completely open. Suppose let G be a group. It's a finite model for BG. Does this imply, now I'm writing the Betty numbers of the group, not of some matrix. These are all integers. And also to this question, there are no counting sums. So there's a difference whether you fix the group and look at all elements of the group ring. So you look at all manifolds having this group as fundamental group, or whether you stay at the group itself and want to investigate the Betty numbers there. But again here, I think it's very likely that this is true. It's very hard to find counterexamples, let's put it this way. Okay, maybe it's a good place to stop here.
Thank you very much. Questions? Patrick.
So, what sort of conditions on G do you think you need for this semi-simple DG condition?
I only need this condition about one on the all set set.
Oh, okay.
I really think that this program which will go through in general. I hope so.
So this is much simpler than Austin's.
Yeah.
work.
Yeah.
Good.
It's clear that if you talk to Austin or Grabowski, look at it, their method can only work if you have infinite if you have no bounds. I should say that it's clear. There's no way of getting their methods to cover a case where you have no bound on the order. Because they always look at find subgroups which are very large, have very small dimensions, and then they can do combinations, and you can't do this here.
And is it easy to prove this G torsion pre-implies skew field?
Yes. So that's what's the idea. So if DG is semi-simple, it means it's a matrix algebra. Yeah, okay. I can only do some step here. Give you the idea. Or with some skew fields. FK. That's relevance here, right?
Okay.
If you now compute K0, this is the product. You can write down to take out the matrices by Morita equivalence as well as the product sign. This is just the formula. But this is Q field, so this is Z. Right. But now the map from this huge direct sum should be surjective. But remember, if the group is torsion free, there's only a trivial group. It gives you one copy of Z, and Z can only map surjectively to this here if n is 1. So at least you see why DG must be a matrix algebra, or with Q field. And then you can, by certain further considerations, figure out it has to be a Q field.
Okay.
And actually for a manageable group, the question is equivalent. So if G is torsion free and amenable, then DG is this Q field exactly if Matthias' conjecture is true.
Michael.
I maybe wasn't listening very carefully, but you were focusing in one direction, trying to prove positive results. But in the other direction, I think you implied that, I mean, if you take all finitely printed groups, which can occur, therefore, fundamental groups of manifolds, that you can get all computable numbers and something.
Yeah, yeah.
But you didn't mention this today.
No, this was of course Grabowski work, where it was very short.
Yeah.
But I'm more interested in spherical manifolds.
Pardon?
I'm interested in spherical manifolds. For me, that's clear. If you take all manifolds, there's the question is you can get probably every computable number even more. But if you stick to a
I
spherical,
thought not more, huh? Why?
not
Because
could be more.
if they're compact and finally presented, then they have to be computed.
I think Grabowski in his paper is not clear at this point, whether he makes a statement that he's not quite sure whether he shows that all computable numbers are contained in there,
Yeah.
but the vice versa I'm not quite sure, because for him the computable number was certain the ideal expression in the computable subset of the integers. I don't think that the combinatorics having a finite presented group gives you this directly, but I have to check this. But I want to point out that I'm interested in spherical manifolds.
Yeah.
And there I think that the conjectures are all true, you get always integers.
Yes, very nice.
By the way, I forgot to mention one important thing, that Peter Linnell proved this program, the case of elementary amenable groups and even more. So Peter Linnell made really a substantial contribution to the TF conjecture.
I mean, I was interested in how, main example, I was interested in its application with the spherical manifold, because that's what came into. But the general question for arbitrary manifold raised,
Then
the answer is all computable numbers appear.
Yeah.
And that, certainly at that stage, it wasn't at all, it wasn't clear to me, it wasn't clear to anyone.
No, this is the work of Grabowski, sure.
Yes.
No doubt about it.
When was that done? How?
Grabowski got his PhD 2011.
3 years
I see.
ago.
Yeah.
3 years
So it's
ago.
quite recent.
12 years.
Yeah, it's very recent. Yeah.
Yeah.
Austrian was 2008, or 9, actually during a program at the Himmel
How's that?
organizing.
Mm.
And Grigorchik must be from 2000 or so, 2001 if I remember correctly.
So the treaty lasted quite a number of years.
Oh yeah, yeah, yeah. And I think that Grigorchik didn't know what to do. Austrian was very clever.
So what was the name, Igor?
Grigorchuk and Zubik.
Grigorchuk, yes.
They were making computation and didn't realize that they had done something more important than I thought.
Mhm.
But Austrian was really, for me, the breakthrough, because he realized that you can have this many subgroups and you can push them up to something which is finally generated or finally presented. And then Grabowski came in with this idea of a Turing machine. But the way how you construct these examples is still, I think, Austrian's idea. That you look at actions on group poets and so on. That is really, I would say this is for me really very surprising.
So these these ones which have arbitrary communal, they have to have lots of subgroups.
Yeah, you have. Otherwise, the program doesn't work.
Yeah.
That's clear. Yeah. And I really think this is a watershed whether
Yeah.
you say you have a bound on the order of subgroups. You see, I can't exclude maybe somebody if you find a counterexample there, but it's much harder. And then you have to have a completely new idea. And I really, I don't know.
But I mean, obviously there are a whole range of more precise questions. What kind of groups, how many
Yeah.
kind of subgroups, what kind of numbers you get out. There's a big,
It's even for the Lamperter group unknown,
yes.
for instance. But this is a different question.
Okay.
If you fix your group,
Yes, yes,
you
yes.
want to know what all the element numbers. That is very hard.
That's right, yeah.
Yeah. There you have no chance unless you are in the bounded case, because then I can predict it. But even for the Lamperter group, I think it's not known. But this is the most elementary example you can think of. This is very difficult. Yeah.
So there's plenty more conjecture left for the young people, huh?
Absolutely, yeah.
Well, on this happy note, I will thank you for both your talks.